Hello and welcome back to Dr. Logic awkwardly does one last logical proof in predicate logic. This time, really, I promise this is the last one. And then we'll get to talking about general strategies for doing these proofs. This one that I picked, I wanted to do because it involves the existential quantifier, but I'm never going to do any existential elimination. I'm going to do it all with quantifier interchange, because that's another rule that we haven't really seen any examples of, and we can do cool things with it. So let me get things started. This time I will write smaller than my previous one, and hopefully everything will fit. So our first assumption is that for every x and every y, if axy, then bx and cy. Second premise, for every x and every y, if either bx or dy, then not axy. And do I have enough parentheses there? Yes, I do. These are two assumptions from this. What we want to prove is it's not the case that there is an x and there is a y, axy. Now, you might look at this and think, oh, look, it's a negation. I'm going to assume the opposite, try to derive a contradiction. As soon as you do that, though, what you would be assuming is this. You've got two existential quantifiers. You would need to do two existential elimination assumptions, and things will probably get very complicated very quickly. So let's do something a little bit more unique. I'm going to start doing universal elimination on my first premises immediately. Even though I don't have any constants yet, I'm just going to pick some. So take the first one. I've got two universal quantifiers, so I've got to eliminate them one at a time. I'm going to start by eliminating the x. It's the main connective. You have to work with the main connective first. So if I do that, I remove the universal quantifier, and then every place where there was a variable that quantifier bound, I replace it with my constant, which in this case is little a. So universal elimination on line 1. And now, because I still have another universal quantifier, I can do the same thing. Now, I could pick the same constant because the quantifier holds for everything, but I'm actually just going to pick a different one because I can. So I'm going to say that AAB implies either BA, or sorry, it implies both BA and CB. So universal elimination on line 3 because I'm getting rid of the for all quantifier. Now, what would happen if AAB were actually true? Let's find out. Suppose it is true. So here's an assumption, and at this point, I'm making this assumption because eventually I know I want to get the negation of it. So I'm doing this for negation introduction. It might not be completely obvious to you at this point how I know that I can make this assumption. Well, I mean, I can make any assumption I want, but you only want to actually make an assumption if you know what rule you're going to use to get out of it. But look up here at what our premises are saying. This one says, well, if you've got AXY for any x and y, then you've got BX and CY. Separate out the BX. Well, if you have either BX or DY, then what do you get? You get the negation of what you started with. So I know that there's a contradiction hidden in there. Now, I just need to pull this contradiction out. So I assume the antecedent of line 4, and therefore I can derive the consequent BA and CB through conditional elimination, lines 4 and 5. That very same kind of strategy that I talked through, I can now replicate at the level of the propositional logic. So extract the relevant conjunct BA through conjunction elimination. And then I can say BA, or who cares? It doesn't really matter what. Let's just say DB. I'm going to add this disjunction through this disjunct through disjunction introduction. And now I have something that would give me the antecedent of a conditional if I can actually get a conditional that doesn't involve variables but involves our constants. So universal elimination on line 2, replacing the, I'm going to replace the x with a. So we still have the for all y, but then either BA or dy implies not a y. So that's universal elimination, line 2. Now I can do it again, and I want something that is going to match kind of the antecedent that I've defined in line 8. But importantly, in order to get a contradiction with AAB, I need to get not AAB. So it's a good thing that I actually used constant B here in line 8, because now I can do my elimination of this second quantifier. And now I know that if either BA or DB, then it's not the case that AAB. So universal elimination, line 9. Well, we have a conditional at line 10, the antecedent at line 8. So I can do conditional elimination, 8 and 10, to get not AAB, which contradicts our original assumption. Woo! That's what we wanted. So I can introduce the negation, citing the subproof from lines 5 to 11. But we still need to get to something that looks like this. It wouldn't help if I started adding existential quantifiers, even though I could, because of where the negation is. I need to eventually get the negation all the way out to the end. But the nifty part is, if you look at the assumptions that line 12 depends on, you go back up and you see there are no constants involved. That means that our choice of A and B here was arbitrary. I could have written down any other choice of letters I wanted. I didn't have to use A and B. I could have used E and F, and this proof still would have worked. So I am in a position where I can do universal introduction, not just existential. So I'm going to put on a for all y quantifier, and then every place where I have B, I'm going to replace it with y. So universal introduction, line 12. What is it that I need to check? I need to check that the constant I'm generalizing on doesn't depend on any of the assumptions, doesn't occur in any assumption that line 12 depends on. But there are no constants in my assumptions, so I'm good. I don't even have to check again now, because since there are no assumptions that contain constants, no constant that I use will be contained in one of the assumptions. Now, I've got one quantifier, but it's kind of the wrong one. But I've got a negation too. Quantifier interchange tells me that I can move the negation to the outside, change the type of quantifier, and write down not exists y AAY. So that's quantifier interchange on line 13. I can do this again. So I'm now going to do universal generalization on A. That gets me for all x, not exists y, a x, y. Universal introduction on line 14. A doesn't occur in either premise 1 or 2, so I'm allowed to generalize on it. And now I can do the quantifier interchange one more time to get not exists X, exists Y, AXY, quantifier interchange, line 15, and would you look at that, I managed to get the proof to fit on a single sheet of whiteboard. So I could have done it by assuming this existential formula without the negation. All of these proofs that I do can be done in multiple different ways. In fact, I've already had a couple of people leave comments on earlier videos saying, why didn't you do it that way, Dr. Logic? And basically the answer generally is, I didn't think of doing it that way. Or maybe the answer is, because the way I picked illustrated something neat. However, no one way is privileged over another way. Some ways may be shorter, some ways may be longer, but there is a proliferation of different appropriate proofs for any one of these examples that I've been doing. In the next video, I will talk a little bit more about like how to find a proof if you don't kind of immediately see the way that it can go. A lot of the propositional proof strategies, you'll see that we've already been using them. So you need to prove a negation, assume the opposite, et cetera, et cetera. But there are a couple of things that I can add for how to deal with the quantifiers explicitly so we can kind of build up our algorithm into something that if you are ever stuck when doing one of these propositional proofs, hopefully you can go back to the algorithm and say, help me, Dr. Logic, you're my only hope. And the algorithm will tell you, hopefully, what you can do. So that will be one of our last videos on predicate logic proofs for now. There's a lot more that you can say, but I will save that for another time. Take care. Cheers.